Salam doctor, my name is Siah YIh Hoong and today I'm going to present on my experiment 5, which is the voltage regulators. So in terms of voltage regulators, we have known that there is a few types of voltage regulator, which is the series regulator, the shunt regulators, and also the switching regulators. What is a voltage regulators? A voltage regulators is actually a type of circuit that provide us a constant voltage output, essentially independent with the voltage input, also the output load current and the temperatures. And also it is a part of the power supply. And we can see that here's a voltage input. The voltage input is actually connected or coming from the generator station. And after that, it will undergoing a transformer stations and also smoothing process. And it will reach the regulator process right here. Or this will connected in with batteries. So a regulator usually contain a transistor, a resistor, a Zener diode, and the IC. In this lab, we're going to use LM741. So, but in these simulators, we don't have LM741. So we need to include ourselves, which we just need to type this command and then right click and pick the values into LM741/NS. And I believe that I have shown these procedures in lab 2, which is the earlier lab demo. And I will skip these procedures in this lab 5 because the process is quite long and I think it will be boring if doctor continue listening to the same things, right? So I will just skip it. Let us take a look on the series regulators. The circuit as shown in figure 3, and we're using LM741 and 2 resistance as a voltage dividers, and here is another resistance, and we have a transistor of 22221, and then here is the output voltage, and here connected into input voltage. So because of this is the series regulators, it will be connected with series. It will be connected in series with load, which means that here will be a load right here, and it is series with this whole circuit right here. So how these voltage regulators work? As we can see that here's a Zener diode right here. Unfortunately, the LT spice don't have 5.1 breakdown voltage of the Zener diode. Therefore, doctor have given us a range, right? The range is 5 until 7, I think. And I have chose 6.2 voltage of the Zener diode. So after, for the whole process, I will use 6.2 here. So yeah, I have note down right here, so doctor can refer. Okay, just like this, right click, and here's a 6.2. Okay, what is a Zener diode? So a Zener diode is actually helping us provide us a reference voltage to the IC. Oh yeah, before that, we need to take care of this input because for shunt regulators and series regulators, the input is different, right? One is the reference voltage is connected into the non-inverting input, but for shunt regulators, it will be connected into inverting input. This is the things that we need to take care. If not, the whole circuit will be going off the rails. Okay, so this diode will provide us a reference voltage. So when a power supply coming in from this input voltage, it will pass through this resistor and again inside and go inside this IC. Okay, the power supply will be amplified. Okay, and it will treat as an output, and it will pass through this voltage divider. Okay, and after that, it will be treated as a feedback into the inverting input of this LM741. And this will cause it to produce a different voltage. And this difference voltage is known as error voltage. And again, this error voltage will become amplified by this IC and going into the output here. So let's say if my output voltage trying to change, for example, like decrease, it will be detected by these voltage dividers, and it will be treated as a feedback into this IC. And the process right here will result it into a nearly constant output. Yeah, amazing, right? Yes. So the regulations for the shunt regulators is almost the same, just that the input is different. The thing is still same, which the changes of the output will be detected by these voltage dividers, and again it will be sent as a feedback into the non-inverting input. Yeah, that's the difference. And also the shunt regulators is connected parallel with the load, which means here will be a load connected parallelly into this things. So it's something like this. So for example, here's an output. So here will be a load right here. Okay. So this is RL. Okay. But for okay. Mouse. But for how do I? Okay, kind of cringe. Connected. Undo. Okay. So if I'm having the series regulators, sorry. Share. Okay. If I'm having a series regulator, the load will be connected right here. Our load. So we can see that the whole thing is in parallel. The whole thing is in series, right? Do cross. Okay. So after that, let us take a look on the procedure. So the procedure told us to calculate the output voltage when the R3 is set into 10 kilo ohm. So it having the same procedure with the shunt regulators, because repeat the same procedure in the step in the part A. Okay, so I have calculated a few results, which 5 kilo ohm, 10 kilo ohm, 15 kilo ohm, 20 kilo ohm, 25 kilo ohm, 30 kilo ohms as R3. So when R3 is 10 kilo ohm, I will have a theoretical values of 12.4 volt, which can be seen by here. And also for shunt resistor, but shunt regulator right here. And doctor can see that the result for the regulators beginning from 10 kilo ohm R3 have small percentage error, which negative 2.795, negative 2.7958, something like that. And also that's the same thing with the shunt regulator. Yeah, from beginning from the 10 kilo ohm, you see. And the percentage error for the 5 kilo ohm R3 for both regulators is quite high, which is 28% and 19%. That's because of the output voltage might reach a saturation when the simulations going under process. Okay. Yeah. So this is the graphs of the sections A, which the output voltage against R3. We can see that the graph having a slope like this is going down. And for the sections B, also the same, is going down. Yeah, oh, here will be a section B, not A. I think I need to. Yeah, it's a B. I can like that. It's a B. Okay. And this is a graph. Okay, now let us take a look on the simulations. Let me split the screen first because we need the table for section A. Yeah. So this is the section A. And I believe that doctor have already known that we learned how to construct the circuit, as the process of constructing the circuits is pretty simple, which I just need to take the component from F2 and wire up the component by pressing F3. So I think I will just skip the process because it will be quite boring if I show how I construct, right? Because it's a pretty simple things. And the thing that we need to take note is the Zener diode right here. After we pick the Zener diode, for example, like I want Zener diode, and then it not showing what exact right here, because we still need to pick a model for this Zener diode, right? We have so many diodes and we need to pick a model for it. And in this lab, I have chose 6.2. Yeah, right here. So if I want to follow the actual Zener diode that I've used, which is the BZX something. Yeah, this. Okay. But I just did it. And for the transistor, we need to pick a new transistor. And we're going to use this 2 and 2 transistor. Okay. And then for the simulation command, we just need the .op right here, which that we can set from here. Sorry, not this. Simulate, edit simulation CMD, and we choose DC OPPNT. And we need to take note that the text box here, we just only need .op, and then press OK, just like this. And I have already told this right. Okay, so if we follow the procedure we're going to use by using the same circuit, varies R3 from 5 kilo ohm to 30 kilo ohm with increment of 5 kilo ohm, with Vin is set into 15, right? So the input voltage have set into 15 volt. Yeah, the resistance also the same, 1 kilo ohm, 10 kilo ohm, and R3 is the manipulated, right? So at first we're going to set it into 5 kilo ohms. So here's the 5 kilo ohms. And then after that, we just need to run. Okay. And here's the voltage output. And I'm going to minimize it for me to easily look at it. Easy for me to read the values because it appears directly above this window, below this window. Okay. So for the 5 kilo ohms as R3, it will have a result of 13.3743, 13.3743. But unfortunately, we have a theoretical value of 18.6, and which causes us to have a percentage errors of 28.0952. And it's okay because it have already reached a saturation. And let us continue with the 10 kilo ohms. Okay, it will be the 10 kilo ohm and click run. 12.7464, 12.7464. We continue it with 15 kilo ohms, 15 kilo ohms. It will be 10.62222, 10.62222. Okay. And then we continue it with 20 kilo ohms, 20 kilo ohms. 9.56001, we round off. Sorry, 001. Okay, I will make sure I correct this value afterwards. And after that, we run for 25. Okay. 8.9228. 8.9228. Okay, we run for 30. Okay, right. 8.4979. 8.4979. Yeah, that's right. So yeah, okay, the percentage error here is small and here's big. Okay, and the values, experimental values right here, but the theoretical values right here. Okay, the voltage input still the same, the R3 is different, and the V out, and the voltage reference here for this Zener diode. After we get the values, we plot the graph. And now we're going for the section B. What happened right here? Nothing happened. Okay, for section B, still the same, just that we need to have still the same things. We need to include the things because of we having LM741. And the Zener diode, pick a new model, pick a new diode, and I go for 6.2 volt. And the transistors here, transistor is 2N222. From here, pick a new model right here. Okay, the reference voltage is connected with the inverting input, but the voltage divider junction right here is connected to the non-inverting input. And we need the power supply for the VCC and negative VCC for this diode, for this IC to work. Okay, and now we're going to start over from 5 kilo ohms, right? Okay, we run this. Okay, here's the V out, 14.9781. 14.9781 right here, right? Okay. Yeah. Okay, 14.9781. And then we change it into 10. And then we run again. 6.371. Sorry, that's not. Here is the 12.7413 voltage. And then we run for, right, correct, right? It's the same value, right? 12.713. Okay. And then we go for 15 kilo ohms. Run again, and we have the voltage output of 10.6178, 10.6178, 10.6178. And then after that, we run it again with 20 kilo ohms, 20 kilo ohms. Run again, run, and then we will get 9.56, 9.5561, 9.5561. Then we run for 25 kilo ohms. Then we run again, and then we'll get 8.9191, 8.9191. And for the last value, 30 kilo ohms, 30 kilo ohms, and then run. So 8.4944. Okay, that's the whole simulation. And then after that, we're going to get the values, theoretical values, and then we plot the experimental values, the experimental values, and then we plot the graphs right here. That's things. So for the I have already screenshot the output result. Yeah, as a proof that I make this my own. Yeah, so here's a section A. We have 5 kilo ohms, 10 kilo ohms, 15 kilo ohms, 20 kilo ohms, 25 kilo ohms, 30 kilo ohms, and also for the section B, 5, 10, 15, 20, 25, 30 kilo ohms. And all of these will have a voltage reference of 6.2 volt. Yeah. And that's the whole process of this lab 5. And yeah, we just need to take care, like take note, aware of the pin right here because it's having different pin from the LT spice, right? You can see that negative and positive, but for here it's positive and negative. Yeah, that's the thing we need. That's the thing we need to take care of. And I think I have done my demonstrations, and that's all. Thank you, Doctor. Thanks for patience to listening to these demonstrations. Thanks, and yeah, bye-bye.